Welcome to Physics 2212, Lab 3, Circuits. Introduction. The purpose of this lab is to predict how a circuit acts with resistors in series and in parallel, and to use a multimeter to measure current and voltage of a circuit. The model we used for this was the physical circuit in a laboratory made up of light bulbs, resistors, wires, batteries, and so on. The surroundings are everything else not a part of the circuit. For the results, we got the 47 ohm resistor had a potential difference of 0.87 volts, and the 100 ohm resistor had a potential difference of 1.86 volts. The current measured was 17.4 milliamps. For the physical principles of the lab, we had the node rule, which states the current going into a node has to be equal to the current flowing out of the node, as you can see in the diagram represented in the bottom left. For the loop rule, it states that all electric potential differences around a loop must add up to zero, as you can see in the bottom right, with all of it summing to zero. Although super important principles at play are Ohm's law, which is V is equal to IR, voltage is equal to current times resistance, and capacitance, Q is equal to C times V. For part 1 of this lab, we made a circuit in series, which had two batteries, each of them 1.5 volts, two multimeters, and two resistors. For part 1, we found that the current of both 1 and 2 were both equal to 17.4 milliamps. When directed to reverse the connections, we found the readings to be negative, but of the same magnitude of 17.4 milliamps. Next, we found I1 is equal to 2.88 volts, and I2 is equal to 0 amps. We then asked to find the potential difference readings of each component. So for battery A, it was 1.31 volts. For battery B, it was 1.56 volts. For the 47 ohm resistor, it was 0.87 volts. And for the 100 ohm resistor, it was 1.86 volts. The sum of all of this is 1.87 volts. But in theory, it should be 0 volts. This is due to human error, which we will discuss later. Next, the ammeter across the 100 ohm resistor is 51 milliamps, and the ammeter in parallel was 48 milliamps. This is the analysis of the sum. As you can see, it starts up with the two batteries at 3 volts, and slowly declines down till it hits 0 volts, which is the theoretical place it should be at. For part 2 of the circuit, we had two batteries, each of them 1.5 volts, and two light bulbs. Light bulb 1 was 2 volts and 60 milliamps, and light bulb 2 was 2.5 volts and 0.3 amps. For 1, we measured what happened when the capacitor was charging, and we found as the capacitor charged, the light bulb's brightness decreased. For 2, we found as the capacitor discharged, the light bulb's brightness also decreased. The charge time was measured to be 2 seconds, and for the discharge time, we measured it to be 40.95 seconds to completely discharge. Possible errors in this lab were inaccurate measurements from the voltmeter or ammeter. They were probably from the 1950s or so, ancient technology, and I don't think they would be fully reliable. The batteries may not have been fully charged, and that may have affected the calculations. And other surroundings, such as air, were not considered in our experiment, and they could have affected the values achieved. For the discussion, if we charge a capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor reach full charge? So, predicted it would charge much faster because it would flow without any resistance almost instantly. However, this can't happen in real life because there's no such thing as zero resistance. Measured time was much longer than the predicted of 0, as there was resistance from the wire also. Thank you.